So let us begin with the chapter 3, which is on multivariable optimization method. In this particular chapter, first we will go through the introduction. Thereafter, the optimality condition for multivariable function. We will also talk about the convexity, the convex functions and other theorems. Then we will move towards the methods. So as we have two types of methods, first is called direct search method. In this category, we will be going through two important methods. First is called simplex search method, and another is called conjugate gradient method. Similarly, we will go through the gradient based methods. So for example, steepest descent, Newton methods, Marquard's methods, and conjugate gradient methods. So in this category of a direct search methods, we have few more methods, but in this particular lecture, we will be following only these two methods. So let us begin with the introduction for the multivariable optimization. So in the previous chapter, what we found that the objective function was formulated using single variable. But now the objective function is constructed using multiple design and decision variable, meaning that the function will be written as xt, where x will be representing the column vector having size n, and t will be representing the current iteration. So for example, if we want to write xt, this will become x1 to xn column vector, and in the tth iteration. Now let us move to the optimality criteria. This we will be proving using Taylor series expansion. So as we know that for single variable optimization, we use Taylor series expansion for single variable function. So similarly, we also have Taylor series expansion for multivariable function. Before we begin it, let us assume that the function, the gradient of the function, and the gradient of function exist, and all of them are continuous for all values of x, and x belongs to the real space of size n. So let us rewrite. Now here, let us assume that x bar is the minimum point, and the Taylor series expansion at x bar plus delta x can be written as the f of x bar plus the gradient of the function at x bar into delta x. Now, since you may be knowing that if you are going to find a gradient of a scalar function, it will become a vector. So vector transpose this delta x vector, it is nothing but a dot product. Similarly, another term is half times of delta x transpose gradient of a function, then delta x plus the third term. Now here, let us rewrite this equation. So what we will do is in equation 1, this fx we will take on the left hand side. Now let us look at the equation number 2. So this difference of x plus delta x minus the function value of x bar, we are referring this as a delta of x, and then right hand side term. Now since you know that we are solving a problem for a minimization and x bar is a minimum point, so any value of a delta here in equation number 2, whether it is positive or a negative, so this delta x value should always be greater than 0. This particular relationship is similar to what we have used in single variable optimization. Another thing, that since this particular condition is satisfied, it has to be satisfied that the right hand side should be greater than 0. So in equation 2 also the right hand side should be greater than 0. Now if you are looking at this particular term on the right hand side, this is the dominating term, and in this dominating term delta x value can be positive and can be negative. So for any arbitrary value of a delta x satisfying that the right hand side is greater than 0, the only condition which we have is our gradient of the function at x bar should be 0. So this condition is referred to as necessary condition. Now it's the same equation number 2. Now, as we know that to satisfy the greater than equal to sign on the right hand side, the first condition is that the gradient of the function at x bar should be 0. Similarly, if we ignore the other terms, we are going to get that the delta of the function is equals to this particular term and everything should be greater than 0. So this term has a significance and we will see how. Now the term which we have right now, it is quadratic. It means that it is going to be greater than 0 if this gradient of the gradient function at x bar is positive definite. It means that x bar is a local minimum point. If I start this, if I use the Taylor series expansion for a maximization function, what you will realize that the delta of fx should be smaller than 0. In this case, this particular term, which is gradient of the function at x, should be negative definite. In that case, we can say x is the local maximum point. If it is neither positive nor negative, then we can say that x bar is the saddle and the inflection point. So all these three conditions put together will give us the sufficient condition. So let us rewrite all the optimality conditions together. So necessary condition says that a point x bar. So now we are referring this as a stationary point. Why? Because we don't know whether this point is minima, maxima, or the saddle point. So we are saying that x bar is a stationary point if the gradient of the function at this point is 0. The sufficient condition says that furthermore, the point is a minimum, maximum, or an inflection point. So this term H we are representing. Why? Because H will be referred as a Hessian matrix. So if Hessian matrix is positive definite, negative definite, or otherwise. So as I mentioned you earlier, so our objective function is always a scalar function. So when you put the values of x1, x2, x3, x4, it will give you a one value only. So that's why it is called a scalar function. But when you find the gradient of the scalar function, it is always a vector. When you are finding gradient of this particular vector, you will get a matrix. And that's why we call this particular matrix as a Hessian matrix. Now, the point is that our sufficient condition depends on the positive definite condition of the matrix. So how would I know, or we know, that the matrix is positive definite or not? So in this case, the first condition says that if I take any point y in the search space and this y transpose Hessian y greater than 0, then we can say that the matrix is a positive definite. Now you remember that this particular term came when we were proving for the optimality condition, especially the sufficient condition. Or what I can do is, if the matrix is given to us and I find the eigenvalues, if all of them are positive, I can say that the matrix is positive definite. Or the third condition is when all principal determinants are positive, then we can say that the matrix is positive definite. So here you can use any of them to find whether the matrix is positive definite or not. Now here there are two questions. You think about it, you do some little research, and then you find answer for these two questions. So the first question is, what is positive semi-definite matrix? So we were talking about positive definite. Now we are introducing a word called positive semi-definite. Second question is, suppose we have the x bar, which is a stationary point. And if our matrix, Hessian matrix, will become positive semi-definite, then this X bar will remain a local minimum or a not. So you try to find out this question, answer of these two questions. Now coming to the convexity, it is an important property. We should remember that. So first of all, what is convex function? As it is written here, a convex function is said to be convex for any pair of x1 and x2 and all values of a lambda such that the lambda will be lying between 0 to 1. So this is important that you should remember that lambda will be lying between 0 to 1. And x1 and x2 are two any points. So we are not making any relation between them. So if we write function value for lambda x1 plus 1 minus lambda x2, it is smaller than or equal to lambda times of function value at x1 plus 1 minus lambda times of function value at x2. So let us understand with the help of a single variable function. So the blue curve is a function. Now you can see on x-axis we have x1 and x2. We are making this relation as lambda x1 plus 1 minus lambda x2, which is kind of a scaling. Then I get this particular point. Then if I draw a vertical line, wherever it is intersecting the blue line, you will get a function value as f of lambda x1 plus 1 minus lambda times of x2. Similarly, you know that x1 you get the function value if you draw a perpendicular line intersecting the blue curve. Similarly, at x2 you draw the perpendicular line where it is intersecting the blue curve. So those are the function values of x at x1 and x2. Now if you use the same relationship, what you can find, the value will be given on the top. Now you can make out a difference that this particular inequality holds. So this is in the current example, it is function value at this particular point is smaller than the lambda times of f of x1 plus 1 minus lambda times of f of x2. So there will be a one condition when both the values will be same that I will discuss in the next slide. Now this particular relationship we understood graphically using a single variable function. It is important to note that this relationship or the inequality holds good for multivariable function. So this is you can find in the second statement. There are some remarks. First, you have to note that if the negative of the convex function is a non-convex or a concave function. So negative, if you multiply by -1 with a convex function, the convex function will become non-convex or concave function. Similarly, if I have two convex function as f1 and f2, if you add them, the function capital F will remain convex. Now come to the linear function. So you remember that in the last slide, the left hand side was smaller than and equals to the right hand side. But for the linear function, it is equality. Why? Because the linear function will be convex and a concave both. Now the second statement, also look into the figure. You will realize that this is the same curve which we have shown. But if you divide between A to B, the function is convex. From B to C, it is concave. So that's why a one function can be concave and a convex. So we have to be little careful about in which region we are saying that the function is convex. With this, let us move to the theorem 1. Now in theorem 1, we say that a function fx is convex if any 2 points. So now any 2 points means x1 and x2 belonging to the Rn. This means it's a multivariable problem. So x1 and x2 are two vectors. So here x1 and x2 are two vectors. So we have a relationship that the function value at x2 is greater than function value at x1 plus gradient of the function at x1 transpose x2 minus x1. Now here, let us prove this. How we can do it? So this particular relation we know earlier, that is the relation for the convex function. I did a small change here. Instead of lambda x1, I have written lambda x2 plus 1 minus lambda x1. So you can make it out a difference with respect to the previous equation. But our relationship will always true for any form. And then lambda of f of x2, 1 minus lambda times of f of x1. Now let us rewrite this. Rewrite this means we'll take x1 out and plus the lambda term and then all the factors inside the bracket. So f of x1 plus lambda times of inside the bracket x2 minus x1. And on the right hand side also we will rewrite. So here f of x1 plus lambda times of f of x2 minus function value at x1. Now we are rearranging the term. So let us look on the right hand side of the previous equation. So that's this we are writing now. So what we will do is look at this f of x2 in the previous equation. This we will take on the other side, right? So now the term which is left is lambda f of x2 minus x1. So that's why I have written in the rearranging terms. So lambda f of x2 minus x1 should be greater than and equals to. So this is the term f of x1 plus lambda x2 minus x1 minus f of x1. So this term we take it from the other side. Now since lambda is multiplied, so we'll take lambda in the denominator. Thereafter what we will do is we will multiply this x2 minus x1 as well as divide on the right hand side. So if we divide it, this is the equation f of x2 minus f of x1 greater than equal to, and this is the relationship which we got it, divided by lambda times of x2 minus x1, and this is x2 minus x1. Now let us take delta of x is equals to lambda times of x2 minus x1. If we take this, then let us substitute this value in our previous equation. So the previous equation will look like f of x2 minus f of x1 greater than f of x1 plus delta x minus f of x1 divided by delta x, and then x2 minus x1. Just you remember that the delta x is equals to lambda times of x2 minus x1. Once it is done, and if we take a limit of say delta x tends to 0, so you know that this particular term is nothing but the gradient of the function. So we are writing the same term as f of x2 minus f of x1 greater than gradient of the function transpose at x1, x2 minus x1. And this equation and the given in the theorem 1, both of them are same. Similarly, let us go to the theorem number 2. Here, the function value f of x2 is said to be convex if the Hessian matrix is positive definite. So this we have already proved at the time of sufficient condition. We will again go through it. So we are using Taylor series expansion up to 2 terms. So we are writing f of x1 plus h. So this we can write as f of x1 and the Taylor series function up to 2 terms. Now here you remember that h is nothing but x2 minus x1. And let's assume that x1 is the stationary point. If it is going to be stationary point, meaning that the gradient of the function will be 0. Another condition is if the function is minimization problem, if we are solving a minimization problem, so we know that the function value at x2 will be greater than function value at x1. Why? Because x1 is the stationary point. Now thereafter we rewrite this term. So f of x2 minus f of x1, and then we have a right hand side greater than 0. Now in this equation, this is delta of function which should be greater than 0. So that's why we have a greater than sign on the right hand side. Gradient of the function at x1 should be 0. So this term is going to be 0. And we are left with this particular relationship. Now this relationship, as you remember, that this is one of the relationship for a matrix should be positive definite. And therefore, we can say that the matrix is positive definite for a convex function. Now there is a function called strict convex. Now looking at the figure, that one particular figure, the figure on the left hand side, it has a kind of a flat region, but it has a one minima. The second is a very sharp. So in this case, what will happen that if it is a strict function, then the function value of f of x2 is greater than f of x1 all the time for a minimization problem. If this condition holds true, then it's a minimization problem. Just remember that x1 was the stationary point. Now come to the theorem number 3. It says that any local minimum of a convex function is a global minimum. This is a very important statement and we should all remember that. So I'm leaving it to you how to prove it. So how you can prove? You have to prove by contradiction that the function is not global minimum, assume that, and then you use theorem number 1, which the relationship was given. If you use both of them, you can prove by contradiction that the fx is the global minimum. Now look at the quadratic function. Now if you can write any equation in terms of this is a quadratic equation, then if we look at this particular C, so let me tell you about this function. Qx is equals to A plus B transpose X plus half of X transpose Cx. So this particular equation includes all the terms that are required for a quadratic equation for two variables, say x1 and x2. So it can be convex when C is positive definite. So any quadratic function is not convex by default. What you have to do is you have to find the Hessian of the matrix, which will coming out to be C. And if C is positive definite or semi-definite, then you can say that the function is convex. So it is an important statement. You remember that.